At exactly 5:47 in the morning, something happened that no scientist was prepared to explain. A monitoring station near Memphis, Tennessee recorded a number that immediately triggered emergency alerts. That the Mississippi River, one of the largest and most stable river systems on Earth, had dropped to levels that should not be possible in such a short time. Just 12 hours earlier, everything looked normal. Now the river wasn't just low, it was collapsing. Within hours, stations across a 900-mile stretch confirmed the same pattern. This wasn't a localized issue. It wasn't a seasonal drought, and it wasn't caused by dam releases. Nearly half of the river's total water volume, 47%, was gone in just 72 hours. To put that into perspective, past crises took months to unfold. This happened in 3 days. And here's what makes it even more disturbing. The missing water didn't flow downstream. It didn't evaporate. It didn't follow any known natural system. It simply disappeared. As the river pulled back, it began exposing parts of its bed that had been buried for thousands of years. But what lies beneath may be far more dangerous than anyone expected. So the question scientists are now asking is simple and deeply unsettling. Where did the water go? Stay with us for real-time updates and deeper analysis. Subscribe now so you don't miss what happens next. By the time the sun rose over the Mississippi, the reality on the ground no longer matched what people had known their entire lives. Sections of the river that once carried massive cargo ships now looked like abandoned land. Barges sat tilted and stranded, their hulls resting in thick mud where water should have been. The surface of the Riverbed began to crack under the weight of sudden exposure, forming dry patterns that felt completely out of place in what was supposed to be a living river. Along the banks, farmers walked out to their irrigation systems expecting routine checks. Instead, they found intake pipes pulling nothing but air. Pumps that had run reliably for decades were suddenly useless. In some areas, the waterline had retreated so far that it exposed objects no one had ever seen before, dark shapes beneath the mud, half buried, silent and unfamiliar. Communities that depended on the river for daily life were forced into confusion almost instantly. There was no warning, no gradual shift, just a sudden absence. The Mississippi had always been constant. It had always been there. Now it wasn't. And as more sections of the river continued to drop, one concern began to spread faster than the water disappeared. What if this was temporary? If this situation concerns you, leave a comment with the number 9. The timeline of this event is what makes it so difficult to ignore. It begins in the early hours of March 2nd, when monitoring systems near Memphis recorded a sudden drop from -4.1 feet to -10.3 feet. That level of change alone would normally take weeks under extreme drought conditions. Here it happened in less than half a day. As the data continued to come in, stations from Cairo, Illinois down to Vicksburg, Mississippi confirmed the same pattern. This was not a single weak point in the system. The drop was synchronized across a corridor stretching roughly 900 miles. Every reading pointed in the same direction, down, fast, and without any sign of stabilization. By March 5th, the numbers became undeniable. The Mississippi River had lost nearly half of its total water volume, 47%, in just 72 hours. For context, even the historic drought of 1988 took months to push the river to crisis levels. The drought of 2012, one of the worst on record, followed a measurable pattern tied to rainfall deficits. This time there is no such pattern. No precipitation anomaly. No dam release anomaly. No evaporation model that even comes close. The data is clear, and that's exactly what makes it so alarming. As the data stabilized, the concern shifted into something far more serious: scientific breakdown. At a closed-door briefing in Reston, Virginia, one of the leading hydrologists delivered a statement that immediately changed the tone of the entire investigation. He said the numbers do not follow known physical behavior. That is not language scientists use lightly. Teams began working through every possible explanation, one by one. Rainfall data across the basin remained within normal seasonal ranges. There was no upstream deficit that could justify a collapse of this magnitude. Dam release records were checked in real time and showed no abnormal discharge patterns. Evaporation models, even under extreme assumptions, could not account for more than a fraction of the loss observed over 72 hours. Each hypothesis failed under scrutiny. And that is where the situation becomes fundamentally different from any previous river crisis. In 1988, there was drought. In 2012, there was measurable precipitation loss. In both cases, scientists could track the cause and estimate recovery. Here, there is no clear driver, only a result that continues to hold across multiple independent datasets. That leaves a gap between observation and explanation. And in science, that gap is dangerous. Because when a system this large begins to behave outside established models, it suggests that something deeper, something not yet fully mapped, is influencing the outcome. The Mississippi is no longer acting like a surface river. It may be responding to forces below it. By early morning on March 3rd, survey teams began reaching sections of the river where the water had pulled back far enough to expose ground that had not been seen in thousands of years. What they expected was sediment layers of mud shaped by centuries of flow. What they found instead forced them to stop and reassess everything. Large timber structures were emerging from the riverbed. These were not fragments of recent debris. They were deeply embedded, preserved beneath layers of compacted sediment. Within 48 hours, preliminary carbon dating results pointed to an age between 11,000 and 13,000 years before present, placing them deep in the late Ice Age. That alone would have been a major archaeological discovery. But the context made it far more unsettling. These structures had remained sealed underwater and pressure for millennia. Their sudden exposure meant that something had removed that pressure almost instantly. The river had not gradually receded, it had stepped back, revealing a buried landscape in a matter of hours. Researchers began documenting the layout, noting that these were not random deposits. There were patterns, alignments suggesting deliberate construction, or at least organized natural formation. And that raised a deeper concern. If the riverbed is exposing structures from a time before recorded civilization, then what else is about to surface? As teams continued documenting the exposed riverbed, the focus shifted from what could be seen to what could not. Instruments placed near newly formed fissures began registering gas concentrations that immediately triggered safety protocols. Methane levels were rising rapidly and not in isolated pockets. The readings suggested large volumes of gas escaping from beneath layers that had remained sealed for thousands of years. This was not a surface phenomenon. Hydrogen sulfide compounds were also detected, carrying a distinct signature associated with deep organic decomposition under pressure. In normal conditions, the weight of the river keeps these gases trapped below. But with the sudden loss of water volume, that pressure barrier had effectively been removed. The result is a release that is both continuous and unpredictable. Its field teams reported visible bubbling in certain sections, along with subtle temperature variations in the exposed sediment. These are early indicators of active subsurface processes systems that are now interacting directly with the atmosphere for the first time in recorded history. The concern extends beyond immediate toxicity. Methane is highly flammable and a potent greenhouse gas. Hydrogen sulfide, even at relatively low concentrations, poses serious risks to human health. And the source of both is tied to geological layers that were never meant to be exposed this quickly. What was once sealed is now venting freely, and no one knows how long it will continue. By the time ground-penetrating radar surveys were completed along multiple sections of the river corridor, a pattern began to emerge, one that could finally explain where the missing water had gone. Beneath the Mississippi River, extending across significant portions of its foundation, researchers identified vast subsurface voids. These were not small pockets or isolated cavities. They were large, connected cavern systems. It's lying at depths ranging from roughly 40 feet to over 200 feet below the riverbed. What makes this discovery critical is not just their size, but their location. These voids sit directly under the path of the river itself. 3 independent research teams, working separately, arrived at the same working conclusion. The Mississippi is not losing water to evaporation, nor is it diverting flow toward the Gulf. Instead, the river is draining downward into its own geological base, through an expanding network of underground channels. This process is known as catastrophic subsurface drainage. In simple terms, the river is pouring into the ground beneath it. And because these caverns were previously undetected, there is no existing model to predict how fast they can expand, how much water they can absorb, or when the system might stabilize, if it stabilizes at all. As the underground mapping continued, another layer of concern began to take shape, one that extends far beyond hydrology. The fracture patterns detected along the exposed riverbed were not random. When plotted against existing geological data, they aligned with a known and highly sensitive structure, the new Madrid seismic zone. This is one of the most dangerous fault systems in the continental United States. In the 72 hours following the initial drop, seismic instruments recorded 11 microseismic events along this zone. Under normal conditions, that region registers only 2 to 3 detectable events in an entire month. The increase is not just noticeable, it is statistically significant. And more importantly, it is synchronized with the loss of water. Water pressure plays a stabilizing role in many geological systems. When that pressure is suddenly removed, stress can redistribute along fault lines. The rapid drainage beneath the Mississippi may be altering that balance in real time. This introduces a new variable. If the cavern systems below are expanding while the fault zone is becoming more active, the interaction between the two could increase the risk of structural shifts beneath the surface. The river is not just changing. The ground beneath it may be moving as well. As the river continued to fall, The impact moved rapidly from data screens into daily life. Along the Mississippi corridor, entire systems built around stable water access began to fail. Barge operators reported immediate disruptions, with vessels unable to move through channels that had become too shallow within days. Its early estimates placed economic losses at over $800 million in the first week alone. The agricultural sector felt the shock just as quickly. Nearly 40% of American agricultural exports rely on this river system. With transport halted, grain terminals from St. Louis to New Orleans slowed to a standstill. Farmers depending on river-fed irrigation faced an even more immediate crisis. Its intake systems designed to draw from a consistent water level were suddenly pulling nothing at all. In multiple states, emergency water advisories were issued. Communities began restricting usage. Hospitals activated conservation protocols. Schools in affected areas temporarily closed as officials assessed supply stability. What had always been a reliable natural resource was no longer guaranteed. For millions of people living along this corridor, the Mississippi was not just a river, it was infrastructure, and that infrastructure is now under stress. As of March 5th, the most concerning detail is not what has already happened, but what is about to happen next. Its meteorological systems are now tracking a large weather front approaching from the northwest, expected to bring significant rainfall across the Mississippi basin. Under normal conditions, that would be a stabilizing factor. But these are no longer normal conditions. It's the river system that once carried excess water safely downstream may not function the same way anymore. If the subsurface caverns beneath the river are still expanding, incoming rainfall could be redirected into the ground instead of flowing toward the Gulf. That introduces a level of uncertainty that emergency planners cannot model. There is no historical precedent for this. Past crises, whether in 1988 or 2012, followed predictable patterns. Scientists could measure rainfall, track flow rates, and estimate recovery timelines. This time, the foundation of the system itself appears to be changing. And that changes everything. Engineers are now reassessing critical infrastructure built along the river. It's including bridges, pipelines, and facilities that were designed under a single assumption that the ground beneath them was stable. If that assumption no longer holds, the risks extend far beyond water levels. So the question facing experts right now is no longer about how low the river can go. It is about what happens if the system beneath it continues to shift. Because if the Mississippi is no longer anchored to the surface, then its future and the future of everything built around it remains completely uncertain. Subscribe now for continuous updates as this situation develops.